Hello students, today we will do Ampere Circuital Law. Now if you remember in chapter 1 when we were dealing with the electric field, the Gauss Law was used to find out the electric field intensity due to some symmetry. So instead of applying the Coulomb's law to find out the electric field intensity, the Gauss Law was very easy, and the equation for the Gauss law was the surface integration of electric field intensity is equal to summation q upon epsilon naught. So this was a surface integration, and this law was applicable when we have certain symmetry. So it was easier to find out the electric field intensity using this law instead of using the Coulomb's law. There we have a surface integration, and it was equal to the ratio of the charge enclosed. So when we take a summation q, we have taken the charge enclosed in the Gaussian surface. Now in the previous lecture we did a Biot-Savart law. The Biot-Savart law is used to find out the magnetic field intensity. Now Ampere Circuital Law will be more easier to find out the magnetic field intensity at any point, but here also you should have some symmetry of the source. So Ampere Circuital Law is used, so it is used to find magnetic field intensity, or we denote it by B vector. It is used to find out magnetic field at any point due to symmetry. We will see what is this symmetry. It is an easier version of a Biot-Savart law. So instead of applying the Biot-Savart law, Ampere law is very easy to find out the magnetic field intensity at any point. Now let us see the basic concept of this Ampere Circuital Law. Suppose we take a two wire. In one wire the current is going up, and in the second wire the current is going in the downward direction. Generally we have only one wire in our course, so it is more easier to apply this law. But let us see how to find out the magnetic field intensity if we have two wires. Now suppose the question is find out the electric field intensity at any point P. We have to find out the magnetic field intensity at point P. Clearly the point is between the two wires. Now if I want to find out the direction, it will be very easy to find out the direction. Here the current is going up. So thumb rule, it will be like this, circle. So magnetic field lines are formed, and you should know that it form a concentric circles. Now if it is the case, the magnetic field due to this wire is going into the plane of the board. If I take this wire, the current is downward. Again the field lines are formed like this. Again at point P it is going inward. So the resultant, we know that we can apply the superposition principle and we can do the summation. However, how the Ampere Circuital Law can be used in such situation? So the first thing, when we apply the Gauss law, we assume an imaginary Gaussian surface. Here we have to assume an imaginary Amperian loop. You have to consider an Amperian loop. Now the Amperian loop can be considered in such a way that the wire can be enclosed inside the loop or it cannot be enclosed inside the loop. There may be a two situation. So either the wire is inside the loop or the wire is outside, like we have this when we use this, suppose there is a charge q1, q2, q3, while applying this summation q, we consider only those charges which are enclosed in the in the surface. The charge outside was not considered, but at the same time we have noted that the electric field intensity is due to all the three charges, whether they are inside or outside the surface. Similarly, suppose I take this two wire, I have to find out the magnetic field, let's say point P or point Q, that is outside, or a point R. We have to find out at any point, it is between the two wires or either side of the point. Suppose I see this current carrying wire from the top. So let us see the top view. What will happen if I see it from the top view? The current is coming out. So I represent this wire by a dot. So this is the current which is coming out. For we have assumed now it is coming out. So this wire which was held vertical is been held like this. Now the current is coming out. So current was going up, now it is coming out. So it is a top view. The current is coming upward. If I see it from the top, the current is going down. I draw it like this on the board. So it is going in. So current coming out, current going inward the plane. Or you can take this diagram also. Now, in order to find out the magnetic field intensity, now let us take a point P here. Anywhere. But let us take the point here. So first step to apply the Ampere Circuital Law is to consider a loop. You have to consider a loop in such a way that a point P is on that loop. Now this loop is simply a circle. So it is an open surface. There we have a closed surface. Here we have a open surface that is simply a circle, a ring like this. This imaginary loop is called as Amperian loop. This is called as Amperian loop. So here, if my point P is here, I draw this Amperian loop. This is my point P. Now, the second step is, after considering this Amperian loop in such a way that a point P is on that loop, we divide this loop, because it is an open surface or a circle, we make a line elements. So we divide this this loop or a ring into a small line element. Let us say this is dl vector. So this is your dl vector. In this diagram, I divide this loop into a small line element. See, the direction of the line element can be taken either in anti-clockwise or a clockwise direction. It will not make any difference. So if a system consists of more than one wire, here we have two wires. So while taking or dividing this loop into a line element, the direction of line element can be taken as per our choice. If we have a one wire, the case is very simple. We will see that also. So in this situation, I have divided this Amperian loop into a small line element. Now, I do the line integration. Now there will be the magnetic field at this point due to wire I1. magnetic field intensity will be there due to the wire I2. If I consider only this wire and the point P is here, so magnetic field is going inward. So this is wire 1, point P is lying here. So the magnetic field intensity of this wire, so point P here, so it is going inward. If I take this wire, its magnetic field is like this. For this point, it is coming outward. So both the fields are in opposite direction. Here, if I take a point inward, we have seen both the fields were in the same direction. So now both the wires are enclosed in this Amperian loop. This dot and cross represent the current. Magnetic field due to this wire was going inward. Due to this wire it was coming out. We have to find out the magnitude of the magnetic field intensity. Then you can apply the superposition principle, or directly from the Ampere Circuital Law we will find out the magnetic field intensity. So if I have to go for a Biot-Savart law to find out the magnetic field intensity, I will individually find the magnetic field intensity and then apply the superposition principle. Or I can directly find out the magnetic field intensity due to Ampere Circuital Law. So we have divided this line element. Now what Ampere says, the line integration, remember it is a line integration, here we have a surface integration. So you do the line integration of the magnetic field intensity. We don't know what is the resultant of the magnetic field intensity. So because for one wire it is going inward, for other wire the magnetic field is coming outward. So we have to take the line integration either in anti-clockwise and clockwise, that is your choice. Now this is equal to, here we have 1 upon epsilon naught. So in this branch 1 upon epsilon naught is replaced by mu naught. Total charge enclosed, that was a source. Here the source is a current. So it should be summation I. We call it a current enclosed in the Amperian loop. So here instead of using the symbol summation I write IE. Here IE is equal to current enclosed in Amperian loop. Now both the current are enclosed in the loop. Both the current carrying wire are inside the loop. Remember, the magnetic field intensity at point P is due to all the wires. If I consider a third wire, suppose it is outside this Amperian loop, the magnetic field of that wire will be there at the point P. But while using this side of the equation, we have to take only the current which are enclosed in the Amperian loop. So B is due to all the wires, whether the wire is inside the Amperian loop or outside. But when you consider a current, it should be only due to the current which are enclosed in the Amperian loop. Now this is the situation IE. So if there are two wires, the direction of the current is opposite. So we have a sign convention for the current, that is summation. It is actually a summation I, or it is represented by E. So there is a sign convention for IE. Now we have to do the line integration in the form of line integration of the magnetic field intensity. Now what I will do is, to determine the direction of the current, we take the help of a right hand rule. We curl our hand in the direction of the current elements, line elements. So here I have taken the line element in an anti-clockwise direction. So I will take a line integration. I will call my hand or my fingers in the direction of the line element. So my thumb is pointing outward. So thumb is pointing outward means the current which is coming outward should be taken as positive and the other current should be considered as a negative. So here I will replace this as I1 minus I2. I will replace this IE by I1 minus I2. If I have taken this in a clockwise direction, then I will curl my finger like that in the direction of the line element. So thumb is pointing inward. If thumb is pointing inward, then all the current in the direction of the thumb should be taken as positive. So I2 should be considered as positive, I1 should be considered as negative. Now this convention is helpful when we have two wires. Generally we have one wire only. So in that situation, the question will not arise whether you have to take a plus sign or minus sign. We will make a symmetry or a situation like this where this confusion does not arise. However, we started with an example of two wires. So sign convention for current. So what is the sign convention? We call the fingers of the right hand. We call the fingers of right hand in the direction of the line element. So the direction of the thumb will give the direction of the current. So whatever is the direction of the thumb, that current should be taken as positive. So we have to take the help of the right hand thumb rule, and the direction of thumb will give you the direction of the current. So we have to curl the fingers of right hand in the direction of line elements. So curl the finger of right hand in the direction of the line element. The direction of thumb gives the sense, the direction of thumb gives the sense in which current is taken positive. So the direction of thumb gives us the sense in which the current is taken as positive, or in whatever direction the thumb is pointing, you take that direction of the current as positive. So if your thumb is, I can apply in this diagram also, so anti-clockwise, my thumb is upward, so all the current in the upward direction will be considered as positive. So for this diagram, Ampere Circuital Law can be written as B dot dl is equal to mu naught I1 plus of minus I2. So generally we write this as plus of minus I2. That is, we did the summation of the current. So this is line integration. So it is a line integration, or either you write L or closed integration it is. So it becomes mu naught I1 minus I2. So this is how we apply the Ampere Circuital Law. Now we have a dot product here. You have a dot product of B and dl. So Ampere's law will be more easier while considering the Amperian loop. We know that if I remove this dot, there will be an angle between B and DL vector. So the Amperian loop is chosen in such a way, you have to choose an Amperian loop in such a way that either B is tangential to the Amperian loop. So if B is tangential, so this is the situation, this is your line element. If I consider B to be tangential, so what will be the angle between DL and B? It will be 0, and cos 0 is 1. So it will be easier to solve this side. To understand or to remove this dot, it is better, or it will be more easier if the Amperian loop is taken in such a way that the magnetic field is tangential to the Amperian loop. At any point on an Amperian loop, B should be tangential and it should be a non-zero constant. So this side can be easily solved, or B should be normal. So if again B is normal to DL, then the angle would be 90. Sin 90 is 0. So this side becomes 0. Or the third case is B vanishes. B vanishes matlab B itself is 0. So if you are taking the Amperian loop and there is no magnetic field inside that Amperian loop, then also this equation can be used. So if there is no magnetic field at point P, I say there is no magnetic field. So this side becomes 0. So I1 is equal to I2. So this is how it may be possible that a resultant magnetic field at any point P is given as 0. It means if it is the 0, then I1 should be equal to I2 in this situation. So there are certain points you have to remember while considering an Amperian loop. So to apply Ampere's law, it should be kept in mind that number 1, B vector is tangential to the, so B vector is tangential to the line element or is tangential to the point on Amperian loop, and it is non-zero constant. So one is B is tangential to the line element. So this is how to apply Ampere's law. It should be kept in mind that, or you can say, or Amperian loop is chosen in such a way that B is tangential to the line element or the point on the Amperian loop. So what this is the case here, theta will be 0. Second, B is normal to point on Amperian loop. So in this situation, B dot dl will become 0 because the angle would be 90 degree. And third situation may be B vector vanishes. The resultant magnetic field itself is 0. And if the resultant magnetic field itself is 0, then this side of this equation becomes 0. So I can easily find out the relation between I1 and I2. So this is Ampere Circuital Law for 2 wires. So you have to simply remember that if you have to apply an Ampere Circuital Law, the first step is choose an Amperian loop. Now when you are choosing an Amperian loop, it becomes very easy if these are the situations. So choosing an Amperian loop is in our hand. So when we choose an Amperian loop, we have to take care that either B should be tangential, normal, or B does not exist there, or B is vanished. Then after choosing the Amperian loop, we divide that Amperian loop into a small line elements. It is an open surface. Open surface means it is a circle. Then we find out the sign convention for the current if there are more than two currents in the Amperian loop. So you count the finger of right hand in the direction of the line elements. The direction of thumb gives the sense in which the current is taken positive. In which the current is taken positive. So you have to remember that if your thumb is upward, the current in upward direction should be taken as positive. So we have taken this example here. Now let us extend this Ampere Circuital Law to a single infinite long wire. So let us consider a long wire, infinite wire. And if you remember, in the Gauss law, we have divided this wire into a small line elements, and the current was flowing through each element, and it was referred as current element. Then we did the cross multiplication of current element and the displacement vector. So we found the magnetic field intensity at any point due to a small element, and then you have to do the integration. Here while applying the Ampere Circuital Law, this integration becomes very easy as compared to the Gauss law. So let us consider this infinite long wire and let the current I is flowing through it. Now we have a single wire only. Suppose you have to find out the magnetic field intensity at point P, and the direction can be easily determined by a right hand thumb rule. So that we have already seen that the electric field intensity at this point will be going into the plane of the paper. So if I want to represent the direction of magnetic field intensity, it should be cross. Again, take the distance of this point to be R. Now to apply the Ampere Circuital Law, the first step is we will consider an Amperian loop. So this is an Amperian loop. Now this is an Amperian loop. Now I have to divide this Amperian loop, which is an open surface, into a line elements. Now the question arises whether the line element should be taken in clockwise or anti-clockwise direction. Now you have a single wire. We know we have to do the dot product. We have to do the line integration of magnetic field intensity, and it is a dot product. So either the angle should be 0 or 90 degree, or B should be 0. Here B is not 0. Now if the point P is lying here, and if I apply the right hand thumb rule, the magnetic field direction is circular. This is the magnetic field, and at this point it is going inward. And if I talk about the direction, it is forming a circle which is anti-clockwise. So whatever is the direction of the magnetic field intensity, here this is anti-clockwise. So I will take DL also anti-clockwise. So what will happen? The magnetic field, we have seen earlier that the magnetic field intensity should be tangential to the point. So here B becomes tangential to the point. So B is also along the tangent. So here the B is also along the tangent, and our line element is also along the tangent. That is, theta will become 0, and it will be easier for us to find out the magnetic field intensity. So if a magnetic field line or the magnetic field is circular, we divide this Amperian loop, this is Amperian loop, as well as the shape of the magnetic field also. So we divide this in the direction of the B. This is your line element. So now it will be easier to remove this dot product. Now we apply this Ampere Circuital Law. So I will write this as B dl cos of 0. So this is the advantage of the Ampere Circuital Law, or this is the advantage of an Amperian loop. We talked earlier that the Amperian loop should be chosen in such a way that the B vector is tangential or normal. So here we have taken the Amperian loop in such a way that B is tangential. So the angle becomes 0. Now this is equal to mu naught. IE means the current enclosed in the Amperian loop. Here we have only one wire. So one wire is enclosed, and again we have to see the direction. So what will be the direction? Here the DL is in anti-clockwise direction. So I will curl my fingers in anti-clockwise direction like this. The thumb is pointing upward, so current in upward direction should be taken as positive. So this is I. Now if I take DL in opposite direction, suppose you take this DL clockwise. So what will be the angle? 180. So here you will have a minus sign. You will have a minus sign. Now you will this minus sign should be replaced by the minus I there. You will again curl your fingers in the direction of DL. So it is more easier if we take the direction of B vector in the direction of the line element, or B is tangential. Here it is, this is the symmetry. This is the easy symmetry. So if I change this DL should be changed to this direction. Suppose you take a opposite. Suppose you take opposite. So there should be a minus sign on this side, because the angle will become 180 degree. Now this can be written as B is a constant, line integration of DL, that is equal to mu naught I. So DL, 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 if R is a radius, it becomes 2 pi R is equal to mu naught I. So B is equal to mu naught I upon 2 pi R. So that is B is inversely proportional to R. So as you move away from this wire, the magnetic field intensity will decrease because it is inversely proportional, and if we come near to it, it will blow up, it will the intensity will increase. So this is the Ampere Circuital Law for a single infinite wire. So this is the magnetic field intensity due to infinitely long wire. The convention should be clear, the steps should be clear, that take first an Amperian loop, divide it into a line elements, that is DL. The sense of this DL will give you the direction of the current, the thumb pointing in the direction, all the direction of this thumb will always give the sense where the current should be taken as positive. So if there is only single wire and we know the direction of the magnetic field intensity, it is better that B is taken tangential, so theta remains 0. If you take opposite of that, that is, if you take DL to be clockwise, then here you have to write cos 180, because we know the magnetic field intensity is always determined by a right hand thumb rule. So here comes a negative sign. Then I have to find out the direction of this IE enclosed. So I rotate or I curl my fingers in clockwise. So all the current in the downward direction should be taken as positive. Here the current is going upward. So I will put a minus sign here. That minus will get cancelled. Again you will get a same magnitude. Now what is the main points about this? We have a symmetry. Suppose I take another point, say Q here. I have to find out the magnetic field intensity. Again, the Amperian loop will have a same radius. So, if I take another point R, again Amperian loop of same radius. So, what will be there? The magnetic field intensity will be same. So, this Amperian loop is drawn like this. It is a cylindrical symmetry. It is a cylindrical symmetry. So the magnitude of the magnetic field intensity at any point, either you take a point, different points, say P dash, Q dash, which are at the same distance from the wire, the magnitude of the magnetic field intensity will remain same. And if I take the point differently, not on the same Amperian loop, then it is a cylindrical symmetry. So one Amperian loop, then second Amperian loop, third Amperian loop, fourth Amperian loop, we have an Amperian loop. So one important point is the magnitude of B vector is same at every point on the loop. At every point on the loop. So the magnetic field intensity at any point on this loop is same. Also, if the points are at the same distance from the R, so force at every point on the circle or the loop will be same because that radius is R. And if we consider the different points at the same distance, then also it is a cylindrical symmetry. So magnitude of B is same at every point on the loop. Also, the magnitude of B vector at distance R is same. That is called a cylindrical symmetry. That is called cylindrical symmetry. So this is one point about the infinite long wire. Then the second point is the magnitude of the magnetic field is same, that we have seen. Now the wire is infinite. The wire is infinite, but the magnetic field intensity at a distance R or a circle of radius R is finite. So the magnetic field intensity is finite, the wire is infinite. So what is the important point about this is the magnitude of B vector is finite, though the wire is infinite. So the wire is infinite, but our magnetic field intensity at a distance R is finite. Then next point, the direction of magnetic field intensity, for we are talking only about the single wire. So the direction of B vector is along the tangent of circle, or you can say it is along the tangent of a loop. So magnetic field intensity, if we have a wire and the distance is R, so the magnetic field intensity is along the tangent, that we already know. So it was found that when an iron filings is spread around a wire carrying current I. So in the starting we have seen that if we have a current carrying wire and if you sprinkle iron filings, they arrange themselves in a concentric circle, and as we move away the intensity decreases, and as we come near to the wire the intensity blow up. So the magnetic field lines So magnetic field lines, so the magnetic field lines form closed loop and concentric circle around wire. So the direction of B is along the tangent of a circle, and the magnetic field lines form closed loop and concentric circle around the wire. And the last, we know the direction of B vector is found by right hand thumb rule. That we know, we have applied the right hand thumb rule, and we know whether the magnetic field is going into the plane of a board or it is coming out. So this is all about the magnetic Ampere Circuital Law, where it is much easier to find out the magnetic field intensity. Now if this point P is on the axis of the wire, then we will see what will be the magnetic field intensity. It should not be infinite. Remember that it should not be infinite. When we come on the axis of the wire, here we have assumed the wire is thin and it is infinite. We will see a situation in an example where this wire will have certain thickness, and we will find out the magnetic field intensity inside, outside, or on the axis of the wire in the next lecture with the help of an example. So we wind up our lecture today. Have a nice day.